All right. Good call. Thank you. All right. So those are the two that we've seen before, and you might not. I mean, I remember this actually from like a homework problem where you had to graph them, like the numerical derivative and the derivative of cosine x. I think we talked about in class maybe. I mean, we didn't make a big deal of it at the time, but I'm psyched that a couple of you remembered. And again, I'm not doing a proof. If you want, you can graph the numerical derivative, and that should be a convincing argument, but certainly not a proof. And then the next one I'm going to do needs a little bit of a derivation, so I'm going to start it down here, and then I'll actually, when I'm done, I'll put it right there. All right, so I need a little bit of work. So tangent is equal to sine over cosine. Does that sound familiar from pre-calc? All right. If I want to take the derivative of sine over cosine, what's that screaming to you? No, I mean it could be, but quotient rule. It's a quotient, right? So if I want to take the derivative of the quotient, I do low d high. What's the derivative? Cosine. Minus high d low, the derivative of cosine. Negative sine. All over. Now I'll do it. I'll write it like this: cosine x quantity squared. But some of you said it's cosine squared x, so I'll actually write that. Cosine times cosine. Cosine squared x. Plus sine squared x. That should be ringing a bell. Sine squared plus cosine squared, I think, is a Pythagorean identity, right? So that's 1. So, look, the derivative of tangent's 1 over cosine squared x. And we get that by the quotient rule. You don't have to, but you can write it like this, right? 1 over cosine is secant, cotangent, cosecant. You remember like those functions. You actually don't, since they're reciprocals, you don't necessarily need the secant function because we have 1 over the cosine function. But it's just a different way of saying it. Is that all right? David?
Do you do cosine apostrophe x to do like a derivative or something, or just you have to still do the derivative thing?
You can't do cosine apostrophe x. That's, I think, weird notation. Okay. You can either say, y equals sine x and the derivative equals cosine x, or you can use Leibniz notation to show it. Leibniz notation is a little more compact, I think, but Newton's notation is fine too. It doesn't matter. I think we do some problems. Is that all right? All right. Oh, this is horrible. Should have told you to close your eyes. All right. Cosine 4x. Julia? Where's the 4 from? It's the chain, right? What are you doing to x? Times by 4, and then cosine. That's a chain rule. That's a composite function. Gosh, this is great. I totally didn't get this reaction in my other class, and I enjoyed this reaction so much more. It's really good. It's like, oh, it hasn't left. It's not going away. It's like an annoying uncle that visits and won't leave. The chain rule. All right, Morgan.
So would it be cosine e to the 2x times e to the 2x times 2?
Yep.
Brilliant.
So where did the e to the 2x come from, Morgan?
That's the derivative of the inside, and the 2 is the chain from the derivative of the inside.
Right? So the chain of 2x. So what are we doing to x? We're multiplying by 2. E raised to the sine of. 3 composites means 2 chains. Question, or you want to do the next? All right, hold on. Are there any questions about those first two? All right, let's give it a shot, David.
That'd be
All right, so you're going a little out of order, but you want to say it's cosine 3 theta times e to the sine 3 theta.
No, wait. Time out.
Wait.
Times 3.
Wait, yeah, times. No.
No.
The
Times.
derivative. No.
Times 3.
No, that.
You put it in order, so then it makes sense. So once you do the derivative of e first or whatever, like e to the sine 3 theta, then times
All right, so the question is, do we need a times 3?
No.
I hear some yeses, I hear some nos. All right, so let's talk about what are we doing to theta? Times by 3, then times, take the sign, and then e to the. So there are 3 things that we're doing, and as we differentiate, we need to go backwards. So the first thing we need to do is take the derivative of e to the, then sine, then 3 times. What's the derivative of 3 times theta? 3. We need that 3. That 3 is important. And if you want David's notation, sort of putting the 3 cosine 3 theta, putting the chains out in front, that's totally fine. Katie Rayner, you want to try 4? You sure? Alicia, you want to try 4? Cosine. Don't say times. Of. So the cosine of cosine theta, which is not the same as a multiplication problem. Okay. And I'm probably going to put the negative sine theta in parentheses so I understand that's multiplication. Yeah, that was good. So what's the derivative of sine? It's the cosine. And then I have to chain on the derivative of what's in the parentheses. And there's nothing algebraically you can do to simplify this. Like, that's it. That's as good as it gets. Don't try to do anything fancy, because it would be wrong.
Wait,
You sure?
Yes.
You good?
Yes.
Question? I was thinking Ian, but Sam, I can ask you too. Arnie, you good? All right. Oh, that didn't work. Close your eyes. Don't look. There's nothing to see here.
I have the World Series music stuck in my head. No, you know the stuff they play on Fox? Yeah.
All right. Who's up? Someone who hasn't gone. Courage for the deed. You gotta try it. Well, I don't know. I saw it's like Katie stabbing Drew. Did you go? Are you sure?
I tried 5.
Did you do one of those?
I attempted to do 1.
Yeah, no, you're done. Dan? All right.
It would be the cosine.
Not yet.
No, I don't know.
You sure? You gave up pretty fast.
All right. It was the
Here, this is the same as sine e to the 3x.
2x.
Sorry, 2x. Sorry, 2x. Sorry, golly. To the 1/2. Okay.
So it would be the
Go from the outside.
No, I mean, you don't have to. Ian.
I would start out with 1/2.
1/2 to the. All right. So that's the outer function. Ian, you want to keep going? Drew, you want to pick it up?
Sure. Times cosine of e to the 2x times 2e to the 2x.
All right. I'm going to remember people in this class are sometimes particular about order. So e to the 2x times 2. So here's the chain. Here's the chain of the chain. Here's the chain of the chain of the chain. So that's a triple chain.
Oh, God.
All right.
I'm totally going to fail this.
Wait.
Can you just go where all that came from?
Yeah. All right. So what did we do to... It's mayhem. What did we do to x? First thing?
Times that 2.
So you work from the inside out. The first thing we did was multiply by 2. That's actually where the 2 comes from. It's the derivative of 2x. What was the next thing we did to x after we multiplied by 2? Come on, everyone. What did you... E raised to that. What's the derivative of e raised to something? E raised to something. What did we do next? Sine. What's the derivative of sine of something? Cosine. That's where the cosine came from. And then we took to the 1/2 power. That's where the 1/2 to the negative 1/2 came from. So we actually looked at the inner function and worked ourselves out from where the chains come from. It's easy once you have the answer. If you don't have the answer, you have to work from the outside in. Okay, so 1/2 times the function of the negative 1/2. Then look at what's in the parentheses. What's the derivative of sine? Cosine. Look what's in the parentheses. What's the derivative of e to the 2x? E to the 2x. Look what's in the parentheses. There are no parentheses. What are you, crazy? We could just write them there, too. Okay? You can try. But I mean, like you...
Thinking this right?
Oh, you want to do the next one?
No,
Oh.
I just want to make sure I have the right thing. Because e to the 2x is in the parentheses. That is the inner function cosine e to the 2x, so therefore that becomes a chain, and then, okay.
Yeah. And it's hard in this particular problem, the way you said it was very nice. E to the 2x is the inner function of cosine e to the 2x, because they're actually a bunch of inner functions. They're a bunch of functions sort of nestled in there. So you said it very nicely. You went. I'm not calling on you. Sorry. Kelly. Wait, sorry. Are we good with 5? Is that all right? It was hard, right? All right. You good with 5? Sure. All right. I'm going to just get this out of the way because I think we're going to need room for... all right. So, Kelly.
I'm trying. So I did the product rule.
All right.
E to the x times cosine 2x times 2.
All right. So first times the derivative of the second. Where'd the 2 come from?
Derivative of the inside.
So that's the chain.
Plus sine the 2x times median.
Yeah. Nice. That one actually didn't seem too bad after we did all those other ones with like super long chains. See? And you would have freaked out if I'd asked that to you like 2 days ago. So see, already the hard ones are seeming like easy and medium now. See, I told you so. Told you so. It's hard. I mean, I know. It's hard.
Can I ask a question?
Yeah.
Why do you take the chain of the cosine 2x, not the sine 2x?
First times the derivative of the second plus the second. Doesn't say anything about the derivative of the second, that one, okay? Did you do one?
Not on this page.
No, someone... Yeah. Did you do one?
Yeah.
Yeah.
Can I ask a question on how
Oh,
to
yeah.
do this one, though?
Oh, no. 7? No.
I'm already talking.
No, I don't know what it
Maybe
is.
you guys can get it. You can make a name to it. You'll get it.
Katie, you want to do it?
Go for it.
All right, good. Awesome, thanks. All right, what do you have?
1 over cosine squared 2 to the 5 and then times 2 times 2 to the 5 and then
No, you're so good. You're doing such a great job. Where'd 10 come from? Wrong rule. So it's the exponential rule. So what are we doing? What's the first, when we plug x into this function, what's the first thing we're doing?
Yeah.
Multiplying by 5. What's the derivative of 5 times x?
5.
That's what we need to chain on.
Okay.
So I have 1 over the cosine squared of the function, then I have the derivative of that, and then I have the derivative of the 5x. A double chain. Question? I can't tell if, first of all, I've never had you this sedate, a ninth period. Usually you're bouncing off the walls, driving me crazy, and you're not. So I can't tell if, you're just tired from staying up late last night, or if you get this and it's great, or you have absolutely no clue what we're doing. Ian, answer to that question?
No, but I have a question.
All right, good.
Okay, so if the derivative is 1 over cosine squared, do we have to do anything with that squared, or no?
No.
This is part of the cosine.
Because the derivatives are only going to come from the original function. So if you look at the function, we have a tangent, we have a 2 raised to, then we have a 5 times. All of the chains are going to come from that. They're not going to come from a 1 over cosine squared, because that is a derivative. All right? Did that help? Okay. Rachel? Yep.
Okay. I have a question about
Oh, yes, go ahead.
when it's stuff like this, are we ever going to have to take a second derivative of x?
So, sorry, I need to... The gateway test is just going to be first derivatives. There's going to be times where, the chapter before we saw how second derivatives told us about concavity and how that was important. So we're going to have to take second derivatives at some point. I'm going to be honest with you. This chapter is about looking at the ugliest functions you can possibly imagine, so that when we actually look at reasonable functions, it's not going to seem bad at all. So, yeah, I would say 7. I'd say actually all of these functions are probably functions you're never going to really run across in application problems that we do next chapter. The applications we do are going to be a lot more tame. But yes, we'll do the second derivatives. So, yes, we have to do it, but yes, it's also going to be, no, it's not going to be as ugly as this. Because I hear what you're saying. This is the product of, actually, this is at 5, and ln of 2, those are just constants. But now we have this product, which could be considered as it's a quotient. It'd just be horrible. It would stink. That was well put. All right, Rachel.
Okay, so use the quotient.
Definitely, good.
So it's low d high, so cosine of x plus a
Low,
times
d high,
minus I d low, so x times negative sine x.
All right, now I put negative sine x to make sure it looks like I'm multiplying. Alternately, you can just put times sine x and change the minus sign to a plus. Okay?
And the a disappears because it's a constant.
Yep.
And then it's all over cosine x plus a squared.
And if I tell you that the functions, it's like y of x, once I tell you that the functions in terms of x, Rachel, you're absolutely right. Everything that's not an x is a constant. Except COS, like C and O and S aren't constants. That's actually the cosine function. Yeah. Are we good? All right. So let me see. I think I'll